Greetings everybody, and today I'm going to be presenting 3 different ways to evaluate this improper integral. So that's the integral from minus infinity to infinity of 1 over x squared plus 1, but the whole thing squared. So let's just jump straight into method 1. And method 1 is going to be using trig substitution, so trig sub. So with trig substitution, we want to think of some kind of trigonometric identity that nicely matches what we have in here. So we want something squared plus 1. And a nice identity that suits that is tan squared of t plus 1 is equal to the secant squared of t. So t is some arbitrary variable or angle you can think about. So notice if we let our x to be equal to the tan of t, then what we have in here is tan squared plus 1, which nicely simplifies down to secant squared. So we know x is equal to tan of t, we can differentiate both sides to get our dx, and that's going to be secant squared of t dt. And now we can plug all of this information back in. We're going to get now, so this is now equal to the integral. We'll worry about the bounds later on, but we're going to have on the inside 1 divided by, and now as I said before, this is going to give us tan squared plus 1, which is secant squared, but we're squaring everything again out here. So in fact, we're going to get secant to the 4th power of t, and dx, that's going to turn into secant squared of t dt. And now how about our bounds? Well, notice that x is starting from minus infinity, so where does t start? From our substitution over here, we want to think of what value of t would give us tan t being minus infinity. So a nice t value that suits that is minus pi on 2, because tan of minus pi on 2 will give us minus infinity. And the same deal for this upper bound, infinity. Tangent of what will give us infinity? Well, that's just going to be pi on 2. And notice I'm choosing t to be on the interval minus pi on 2 to pi on 2. You can choose any interval that's I believe a period of pi of t that you want. As long as it's a 1-to-1, it should work out for this integral. So now this simplifies down nicely. Notice we can simplify this integrand down to 1 over secant squared, but since secant is exactly 1 over cosine, this is the integral from minus pi on 2 to pi on 2 of just the cosine squared of t dt. And now we have to integrate the cosine squared, but that's a little bit tricky to evaluate. Notice that we have a nice double angle formula for the cosine. So if we have the cosine of 2t, that's exactly 2 times the cosine squared of t minus 1. And that's where we're going to get the cosine squared from. Let's add 1 on both sides and divide by 2. And we're going to get cosine squared of t is equal to 1/2 plus 1/2 cosine of 2t. So as you can see, we've rewritten cosine squared in terms of just a single cosine, which is really easy to evaluate. And now this integral will give us, well, the integral from minus pi on 2 to pi on 2 of cosine squared, but that's exactly 1/2 plus 1/2 cosine over 2t dt. And now we can just integrate term by term, which is really quite easy. First of all, integrating 1/2, that's just going to be 1/2. And then we're going to just attach a t to it, and then we're going to evaluate this t from minus pi on 2 to pi on 2. And then same deal for this expression over here, this term, that's going to be 1/2. But remember, we have a 2 inside this cosine, so because we have to use the reverse chain rule when we integrate, we're going to get 1/4. Integrating the cosine, that's just going to be sine of 2t. And you can check that this is in fact an antiderivative, because when you differentiate the sine, you're going to get cosine, and then chain rule, this 2 is going to hop out to the front, and you get 2 over 4, which is 1/2. And this goes from minus pi over 2 to pi over 2. And now all that's left to do is evaluate this thing. I want to take a look at the second term first, because notice if we plug pi on 2 into here, we're going to get, well, sine of pi, which is 0, so this is gone. And then if we plug minus pi on 2 into here, we're going to get sine of minus pi, but that's also 0. That's gone. So in fact, this whole entire second term is irrelevant, contributes nothing. And all that's left is this first term. So we're going to get 1/2, and then plugging pi on 2 into this t, that's going to give us pi on 2 minus the lower bound. Lower bound is minus pi on 2, so chuck that in over there. And pi on 2 minus pi on 2, that's exactly pi, so we get a final answer of just pi over 2. So that is how we evaluate this integral using the first method. We get pi over 2. So that's using trig sub. And now we're going to look at the second method. The second method is going to be probably the longest method. So method number 2, instead of trig sub, we're going to take a look at hyperbolic trig sub. So I'll just write it as hyperbolic trig sub like so. So very similar concept to start off with. We want to think of some kinds of hyperbolic trig identity that nicely matches with what we have in here. And I want to look at the trig identity, or hyperbolic trig identity, cosh squared of t minus a sinh squared of t is equal to 1. And from here, let's add sinh squared on both sides. So we're going to get cosh squared of t is equal to sinh squared of t plus a 1. And in fact, this is basically a substitution, because notice we have something squared plus 1. So if we just let x to be equal to that something itself, which is a sinh of t, then this x squared plus 1, that's going to turn into cosh squared of t. So we have our x being equal to sinh of t. We can find our dx by differentiating both sides. That's this cosh of t dt. And now we can plug everything in. So this is going to give us the integral. Again, we'll worry about the bounds later on, but we're going to get 1 divided by. Now remember, in here, that's going to turn into cosh squared of t because of this identity. And since we're squaring everything, in fact, we're going to get a cosh to the 4th power of t. And our dx is going to turn into cosh of t times dt. And how about our bounds? Well, if you take a look at the sinh function, sinh of what will give us minus infinity? Well, that's just going to be minus infinity, and same deal for infinity. We're just going to preserve our bounds, because if you look at the sinh graph, it looks something like that, and nicely 1 to 1. As we approach infinity on the x-axis, we approach infinity on the y-axis, and other way around as well for minus infinity. So this is now going to give us the integral from minus infinity to infinity of 1 over cosh cubed, because we can make some cancellations, but that's just exactly sec cubed of t integrated with respects to t. Alright, so now from here, what I want to do is I want to call this integral something. I want to call it I. So all of these integrals are the same, so I guess this integral is also I as well. And now I want to muck around with this sec cubed, because that is a little bit tricky to evaluate. What I'm going to do first, so first of all, I is still equal to, I'm going to split that sec cubed up a little bit. I'm going to split it up as follows. We're going to have sec of t times sec squared of t dt. And the reason why I'm splitting this up is because we're going to be using integration by parts, of the di method. So let's do that quickly down here. So we have di plus minus integration by parts. We're going to be differentiating the sec of t, because that's nice and easy to differentiate, and we're integrating the sec squared of t because we know how to integrate that. That's in fact going to turn into tang of t, and differentiating sec of t, that's going to be minus sec of t times tang of t. Alright, and how does the di method work? Well, these diagonals over here, that's going to give us part of the answer, and each of these rows, that's going to be a new integral we're going to be evaluating. So this I now becomes, we have sec times tang, so let's write it like this, and we're going to have sec of t times tang of t, and so we're evaluating this from minus infinity to infinity. And then the second row of this table is going to give us another integral. Notice we have a double negative, so that's going to be a plus the integral from minus infinity to infinity of, well, we have a sec and then 2 tangens, so that's going to be sec of t and then tang squared of t, like so. Alright, and now we want to look at this part over here. We can evaluate this quite easily, because notice a sec of t is 1 over cosh of t, and tang of t is sinh of t divided by cosh of t, and notice that's just exactly sinh over cosh squared. But I want you to notice one thing. We're evaluating this at the bound, so technically we're taking the limit as t approaches plus or minus infinity. Notice that if you graph it out, sinh and cosh, they actually grow at the same rate. So in fact, since we have a cosh squared down here, this denominator will in fact grow faster than the numerator as we go out to plus or minus infinity, which means that this actually goes to 0 as t approaches plus or minus infinity. And you can actually verify this for yourself, probably using L'Hopital's rule, but this part over here definitely goes to 0 as you take the limit as t approaches positive or negative infinity. So in fact, our I, all that's really left of I is just the integral from minus infinity to infinity of this integrand. But I'm going to rewrite that a little bit. I'm going to rewrite this tang a little bit. We can figure out another nice hyperbolic trig identity for the tang squared right from, I believe, this line over here. So if we take a look at this, let's divide everything through by cosh squared, and we're going to get 1 minus, or sinh squared divided by cosh squared, that's tang squared of t. And then this is equal to, well, 1 divided by cosh squared, that's sec squared of t. And we can do a little bit of a rearranging. If we bring the tang squared onto the other side and subtract sec squared on both sides, we're going to get tang squared of t is equal to 1 minus the sec squared of t. And that's exactly what I'm going to substitute in. We're going to have sec squared, or just sec of t, multiplied by 1. So the first part is just going to be sec of t dt. And I'm going to use a linearity of the integral to split it up, because we're going to have two terms pretty much. And then we're going to have a minus the integral from minus infinity to infinity. Now sec squared multiplied by this sec again, because we're distributing, that's going to give us sec cubed of t times dt. Alright, and I want you to notice one thing over here. Remember I said I was exactly this integral of sec cubed of t. This is exactly our I, so this over here, that's our I. So in fact, what did we just find out? I'm just going to go over here for now. We just found out that our I is equal to the integral from minus infinity to infinity of sec of t integrated with respect to t minus I. And remember, I was the thing we wanted to solve for. So we can treat this as like an algebraic expression. We can maybe add I on both sides to bring these two together, and we're going to get 2i is equal to the integral from minus infinity to infinity of sec of t dt. And now we can divide both sides by 2, and we're going to get I is equal to 1/2 the integral from minus infinity to infinity of sec of t dt. And remember, I was exactly the integral we wanted to evaluate. So we have to evaluate this integral now. And this isn't too bad to evaluate. Might look a little bit strange. We're integrating sec, not a very common function we integrate. But what I'm going to do is we're going to be using the exponential definition of sec, and that actually comes from cosh. So cosh of t is e to the t plus e to the minus t divided by 2. So if we want to take a look at sec of t, that's just the reciprocal of this, so 2 over e to the t plus e to the minus t. And let's plug this into the integral. This is going to give us 1/2 integral from minus infinity to infinity of 2 divided by e to the t plus e to the minus t dt. Notice this 1/2 and 2 will cancel it, which is nice. And now we're left with this weird exponential thing going on down here. Ideally, we don't want an e to the negative t, so let's get rid of that by multiplying both the top and the bottom by e to the t. So we're going to get the integral from minus infinity to infinity of e to the t divided by, now e to the t times itself is e to the 2t, but I'm actually going to write this as just e to the t squared, and then e to the minus t times e to the t, that's exactly 1. And we'll integrate this with respects to t. Alright, and you may notice now we can make yet another substitution. If we let, for example, u be equal to e to the t, that means that du is also equal to e to the t times dt, and we have nicely e to the t times dt set up over here. So this whole entire part that I circled becomes du. So now what do we get? We get the integral from, well, let's worry about the bounds later on. We're going to get du divided by, now e to the t is u, but we're squaring that, so u squared plus 1. And as for the bounds, well, we just plug these bounds for t in. So as the t approaches minus infinity, u is just going to approach 0. And as t approaches positive infinity, u is going to also approach positive infinity. So we have the integral from 0 to infinity of du divided by u squared plus 1. And this is really quite nice because we can use the inverse tangent function. This integral evaluates to the inverse tan. So this is equal to inverse tangent of u evaluated from 0 to infinity, and inverse tangent of 0 is 0. Inverse tangent of infinity, well, taking the limit, that's just going to approach pi over 2. And that's exactly the answer that we were expecting. So that is the second method, bit of a long method using hyperbolic trig sub, but there's a nice couple trig identities and integration techniques that are used in this method. So the next method and final method we're going to be taking a look at, saving the best method for last, is going to be complex analysis, my favorite method. So complex analysis. That's not how you spell analysis, but whatever. So method number 3 is complex analysis. How do we solve these integrals using complex analysis? Well, if you watch a lot of my videos, you probably already know what to do. We just first of all define for ourselves a function f of z, which is exactly the integrand, but we replace all the x's with a z, so we have z squared plus 1, but the whole thing's squared. And whenever we define a function, it's always nice to figure out where the poles are, because we can use Cauchy's residue theorem. So we can actually decompose this into some linear factors. So we're going to have 1 divided by, now z squared plus 1, that's exactly z plus I and z minus I. If you multiply those two together, you're going to get z squared plus 1, but we're squaring everything, so let's square both of these factors. And right from this expression, you can see that the poles are z is equal to plus or minus I. So if we plot this out on the complex plane, we're going to get two poles over here, I and minus I. And notice our path of integration, we're going from minus infinity to infinity on the real line. So we're going this way. Let's just consider a finite interval from minus r up until positive r, and later, of course, we're going to be taking the limit as our r approaches infinity. And we want to use Cauchy's residue theorem. So ideally, we want to form some kind of contour that encloses one of the poles. We could take the upper one or the lower one. We're going to take the upper one just to keep things nice and positive. Positive orientation as well, because we want to integrate along the contour in an anti-clockwise direction. So now let's call this whole entire contour C. Let's call this curvy path gamma. And now we can say that the contour integral over C of our function f of z dz is equal to the integral from minus r to r. Now, since we're integrating on the real axis, we can just say f of x dx. And then we have plus the integral over gamma of f of z dz. And by the residue theorem, we also know that this expression is also equal to 2 pi I times the sum of the residues, but since we only have one pole in here, we have one residue at z being equal to I of our function f of z. Alright, and now we just have to evaluate each of these integrals as well as this residue, which we'll do later on. Let's take a look at the first integral. If we just take the limit as r approaches infinity, then in fact this is going to turn back into our I. So this integral in the limit as r approaches infinity, it's just going to turn into our I that we wanted to evaluate. And now I want to take a look at the integral over gamma. We can probably use a quick way to verify that this integral goes to 0 in the limit, maybe using the ML inequality. So the integral over gamma of f of z dz, if we take the absolute value of this, we want to find an upper bound for it, we can say that this is less than or equal to the integral over gamma, absolute value of f of z, absolute value of dz, so just using that integral inequality. And notice if we can find an upper bounds for f of z, let's call it m for example, then this is equal to m times the integral over gamma of absolute value of dz, but the integral along a path of the absolute value of dz, that's exactly just the length of the curve, but the length of this curve is exactly pi times r. R is the radius of the curve, so we have m times pi times r. Another way you could interpret this is as some kind of integral of the speed function, because if you have the dz, if you make the parameterization, that kind of gives you the velocity. But since we're taking the absolute value where we have the speed, and if you integrate the speed, then you get the distance that's traveled along this curve. So that's another way you could think about it. And our goal now is to find this m, this upper bounds for our function f of z. That's not too bad to do. Let's just take a look at the absolute value of f of z. And notice, well, that's exactly the absolute value of 1 over z squared plus 1, but the whole thing's squared. And we can switch the inequalities, not the inequalities, we can switch the absolute values in these powers. So we're going to get 1 over the absolute value of z squared plus 1, but the whole thing's squared. And now we can use the reverse triangle inequality. I'll just write it over here. The reverse triangle inequality says that if we have the absolute value of a minus b, then that's greater than or equal to the absolute value of the absolute value of a minus the absolute value of b. And this is a very nice, because we're taking a look at this from the denominator. So in fact, if we take the reciprocal of both sides, we have 1 over the absolute value of a minus b. Since we're reciprocating everything, we're switching the inequality sign, so this is less than or equal to 1 over the absolute value of a minus the absolute value of b. So in this way we can find a new upper bounds for our function if we can write it in this form. And of course it is in this form, we just have a square, but that doesn't really matter. We can just square everything over here if we want to. So we need it in the form a minus b. This isn't quite in the form a minus b, but we can force it in that form by introducing a double negative like so, so z minus -1, and using this inequality that we have over here, this is less than or equal to 1 divided by, now we have the absolute value of the absolute value of a, which is the absolute value of z squared, and then minus the absolute value of v, which is just 1, all in absolute values. And I want you to notice one thing. Notice that for every single point, every single complex number on this path gamma, the absolute value of that particular complex number is exactly the radius, because it lives on a circle of radius r. So the magnitude of any complex number on the path is r. So we can rewrite this as being 1 divided by the absolute value of r squared minus 1. But notice r is going to go very, very big. It's always positive, very big anyways. We're assuming that r is greater than 1, so it actually encloses this pole. So that means the denominator is always positive, so we can just write this as 1 over r squared plus 1. And I actually forgot a squared here. So this is squared, and this whole thing is also squared. Alright, so what did we just find? We found that f of z is always bounded above by this expression 1 over r squared minus 1. So this is in fact our m. So what did we just find? We found that our integral, absolute value of the integral over gamma, is bounded above by pi times r divided by r squared minus 1, but the whole thing is squared. And obviously if you take the limit as this thing goes to infinity, as r approaches infinity, so as r approaches infinity, obviously the degree of r down here is greater than the degree of r on the top. We have a r to the 4 versus an r on the numerator, so obviously this goes to 0. So the absolute value of the integral over gamma of f of z dz is bounded above by 0 in the limit, so obviously that means that the integral over gamma of f of z dz, since it's always positive here, it must be equal to 0 in the limit as r approaches infinity. So in the limit as r approaches infinity, this integral over gamma contributes absolutely nothing to the contour. So now we're left with I being equal to 2 pi I times the sum of residues, or just the residue at z is equal to I. But what is the residue at z is equal to I? Well, if we take a look at this right hand side, we're going to have 2 pi I. Notice that I is actually an order 2 pole, because if you take a look at this linear factor over here, it's being squared, so it's an order 2 pole. So you have to use the formula for residues at higher order poles. So that's going to be 1 divided by, now we're going to have the order of the pole minus 1, so 2 minus 1 squared, or just factorial. And then we're going to have the limit as z approaches the pole, so as z approaches I, of the first derivative. So this is a second order pole, so we're just going to have the first derivative of, with respect to z, of z minus the pole raised to the order of the pole times our function. So 1 divided by z plus I squared z minus I squared. And notice over here, we can cancel some factors and we can actually take the derivative in here. That's not too bad to do. We're going to have 2 pi I. 2 minus 1 is 1. 1 factorial is just 1. So we're just going to have the limit as z approaches I of, now the derivative of 1 over z plus I squared. Notice that this is a power of minus 2. So we're going to get a negative 2 from the power rule, and then z plus I, and then cubed. So that's the derivative. Don't need to use chain rule because the derivative of the inside is 1. And now we can safely take the limit. So this is going to give us, we have enough space, I'll just put it down here. We're going to get 2 pi I times, well, we have minus 2 divided by, now as z approaches I, we're going to get I plus I in here, which is a 2i, but the whole thing cubed. But this is 2 pi I, and then we have minus 2 divided by 2 cubed is 8, and I cubed, that's just negative I. And as you can see, negative and negative here cancel, I and I cancel, and then we have 2 times 2, which is 4. 4 divided by 8 is a half. So we just end up with pi over 2. And that is, again, the exact answer we were expecting. So that's pretty much all for this video. 3 completely different ways to evaluate this one integral. So hopefully you guys enjoyed this video. And up until the next one, I hope you guys have a wonderful day. And I'll see everyone later. Bye bye.